model we had, and that's the Goodman line, which we said is a predictor of failure. So as long as the points are outside the line, so the line says that all failures will be on that line, but you can see that some points are above the line, which is okay because this part is the failure, right? So, oh, sorry, infinite life, my bad. Infinite life. And this part is the finite life. Now, if you look at these points, then you'll see that for these points, which are away from the red line, it's just predicting that these points are actually the finite life. So these are actually the finite life, but they are in the infinite life region, which means that model doesn't predict, does not do a good job of predicting these points. Okay, and same is also true for these points. So clearly, Goodman line is not the best way of explaining the data. These points also, there's a problem that it is not on the line. So why do we use the Goodman line? We use the Goodman liner or equation because it's simple. It is simple. It is conservative for tension. What that means is that for these points, this line could have been drawn here, right? But then it's drawn on the left side, which means that it sort of predicts that all these points above the line are going to have finite life. And so that basically leads to a conservation in terms of design. It is unfortunately non-conservative for compression. And that is because you can see there are a lot of points which are all over the place. So a better way to draw this line to make it conservative would be to put the line right here. So if you made it, put it not here, but just below this. So then it would be very conservative, that it will predict the data for all the points and not just the points which are above. Okay, so there are issues with the Goodman line. And so what we're going to do is in this section, we're going to see this section is other models that predict infinite/finite life, but only in the tension region. Okay, so it's only in the tension region. The reason we are not going to the compression region is most of the things in machine design and mechanical engineering tend to fall in the tension region and not so much in compression. It's more of a civil engineering thing. So I believe the book has more details on compression, but we only look at the other explanations of these points only in the tension region. Okay, so I'm going to put forth another figure from the book, which sort of gives the different models for different models to predict failure. Here. Okay. Let me just get it, missing it. Okay, so you see a series of lines there, a lot of lines. Okay, these lines are different models which are used to explain the infinite fatigue line in tension region. Okay, so we'll discuss some of these. And what is shown here is, first of all, our reference lines. We've already seen the Langer line. We've seen the Goodman line, which connects SE to SUT. The lines which we'll consider today in this section are the Gerber line, the ASME-Elliptic line, the Soderberg line, and that's it. Yeah, just those three. Okay, and then you can look at the Morrow line and the Walker line. We'll ignore this because it's based on stress factor, which is a different way of modeling the fatigue curve, which we did not do. It is the strain method, which we did not quite discuss in this course. Okay, so we'll not do this. We did the empirical questions, which is stress based. And then SWT Walker is just, I'll just ignore that because it doesn't look like it predicts it well. Okay, so let's review all these criteria for predicting infinite life. And I'll just review Goodman again. I'm just going to put the equations down so it's all handy in one place. So the Goodman line, as you see, connects SE to SUT. We said it's a simple and a conservative line. And so for tension, and it's not so good for compression. Okay, so the equation of the line, which is the failure criterion, is that sigma A, which is now on the y-axis, divided by the intercept, which is SE, plus sigma M, and the intercept on the x-axis, which is SUT, equals 1. So that's how we can model the line itself. Okay, however, what we want to do is we want to use this as a design criterion. So what we, in case of design criterion, we want to find a factor of safety so that the line actually is over here. And so then there's this margin at which allows us to keep away from the actual fatigue line. So we need to replace essentially, so factor of safety is greater than 1. So we replace sigma A with n times sigma A. And this, well, we'll call this NF for the fatigue failure, so NF. And then we'll replace sigma M as NF sigma M. So that just serves to bring the line down, and that way we are on this line. That's a design line, and it's away from the actual failure line. So replace that in that equation above and find equation for NF, which is our design factor for fatigue load. So NF comes out to be sigma A divided by SE plus sigma M divided by SUT, the whole inverse. And by the way, that's not new. We did this last time. So NF is the safety factor for fatigue loads. Okay. Next, we'll get to the Gerber line. And if you look at the Gerber line, it joins the SE to SUT, the same 2 points, but it actually replaces it with a parabola. Okay, it doesn't look like a parabola there, right? It's difficult to see that, but it's actually a parabolic equation. So let's look at the Gerber line next. So what we have on the figure was first, let's draw the two lines which you've seen in this course. So one is the Goodman line, and the other one is the Langer line. So Gerber, yeah. Okay, so that's our Langer line. And then this is the Goodman line. SY, SY, SC, SUT. Okay, so now we just need to draw a parabola from starting at SY and connect, sorry, starting at SC and joining SUT. Not quite a parabola. It should dip like this. So that's the curve line. So what you need to do is write the equation of a parabola and then put the conditions that it passes through SE and SUT. And the equation you get is the equation for the Gerber line. Now, before I write the equation, there are a few things here. It's a parabolic equation, as I said. It's non-conservative near the y-axis. So it's a good predictor near the y-axis, and it's only good for tensile stresses. So when you say non-conservative, it really is something bad, right? It's non-conservative means that it doesn't really fit the data well. However, it's very good as you go further away from the y-axis, so it gets better on the closer to the away from the y-axis. It's okay. And sort of it's nice to have a parabolic equation, because if you go back to the plot I showed you earlier, you see that these points are all strewn over the place. So if you are able to draw a parabola like this, that's not right. So it should be something like this. Then it becomes less conservative than the Goodman line, and that's why there's a new line. Okay, so let's write the equation for it now. So the failure criterion is the equation of the line. It's sigma A divided by SE plus sigma M divided by SUT square equals 1. Okay. Now, how would you use it for design? Well, you'll find a factor of safety such that the actual line, the curve is something like this. Okay, so that factor of safety will ensure that the line is not along the Gerber line, but it's parallel to it. So that constitutes our design equation. Which is the same as before. We take sigma A, replace it with NF sigma A, and take sigma M, replace it with NF sigma M, and then solve for NF. And the expression is, so when you put that in the equation, you'll see that NF becomes a quadratic equation. And to solve for the roots of the quadratic equation, you have to use that formula for solution of a quadratic equation. You'll get two roots. One of the root is negative, and the other root is positive. Factor of safety cannot be negative, so we stick with the positive root. So the positive root is NF equals of, some space for this. SUT square sigma A divided by SC, and then this is the part in the discriminant. So it's 1 plus 2 sigma M SE divided by sigma A SUT. This should be squared. That's the formula. Okay, sometimes it's easier to not use this complicated formula, but to just put this values in the equation and just solve numerically for NF. Okay, next criterion is called the Soderberg line. It's kind of interesting idea here. If you look at this curve, which I showed you, there is the Goodman line, and let me just go a step back into our previous chapter. So we had this Goodman line, and then we had the yield line, right? And so what happened was, in this region, there was some problems that we had to, we saw that the yield line was below the Goodman line, okay? And so we need to make this check with two criteria. We need to check NY and NF. And so what the Soderberg line does is actually connects SE to SY. And when it does so, it uses that. So that is the fatigue life criterion, which means that you no longer need to consider the line turning SY to SY, that is the Langer line. You only base it on this line. Okay, and you can see that it's kind of very conservative in the sense that it misses on this region. Okay, to say that this region is in the finite life region, even though it actually corresponds to infinite life region, but it makes equations even more simpler than using the Langer and the Goodman line. So that's the idea behind the Soderberg line. So next one, third one is Soderberg. Okay, so again we have the Langer, Goodman. So the Soderberg line joins SE with SY. So it is simple, clearly, no need to check yielding. Okay, because of the reason I explained just a while back, and it is highly conservative, so ultra conservative. It's the most conservative line in this whole set of lines we're going to talk today. If you want to find the failure criterion, it's just a matter of writing the equation of the line. So as you see, it passes through the 2 points SE and SY. So the equation for line which passes through SE and SY is SE for the sigma, well, this I should write S sigma A, sigma M. So it passes through SE, so that's the intercept, and sigma M as the intercept SY equals 1. To make to use this as a design equation, what we do is we substitute sigma A as NF sigma A, sigma M equals NF sigma M, and solve for NF. If you do that, NF comes out to be sigma A divided by SE plus sigma M divided by SY raised to -1. Okay, so our last one, and then we're done. So, as I said, these, if you look at the data again, you see that it seems like it's advantageous to have like a curve, right? These points look like they lie on a sort of like a curve, but not a straight line, right? So it might be best to use a curve to describe those points. But at the same time, if you look at the fact that you need to consider the yield line as well as the Goodman line, that is this ambiguity in this region. If you want to escape that, what you can do is you can connect SC to SY, not using a straight line, but using a curve. So if you do a curve, it does both things, which is it accounts for the fact that points lie on a curve, and also the fact that you do not really need to work with the yield line. So the ASME elliptic line is just that. It is a curve connecting SC to SY. So the last curve is we're going to talk is the ASME elliptic line. So let's do all the lines on this plot now. SY, SY, SC, SUT. So that's the Soderberg line. Then we have the Gerber line. And the final line, which is the one joining this point to SEY. So those are all the lines. This is, of course, the Goodman, Langer. So the advantage of this line is that, or this curve is that it is considers yield as well as fatigue. Okay, it is not as conservative as Soderberg. So it does the job of Soderberg, but it does so without being too conservative. Okay, so then how do you find the equation of this line? Well, you know it passes through SC and SY, and we're going to use an elliptic equation, so equation of an ellipse. And then the equation is of this form. So the failure criteria is sigma A divided by SE square plus sigma M divided by SY square equals 1. If you want to use it for design, the same thing we did before. Sigma A is replaced with NF sigma A. Sigma M is replaced with NF sigma M. And then we solve for NF. To do that, you get NF equals sigma A divided by SC plus sigma M divided by SY square. And the whole thing has to be raised to negative half. So that's it. So we have 4 criteria for design, and the use of this will depend on how conservative you want to be with respect to your design. So when usually the way this works is, the bigger the factor of safety, the heavier your design is going to be, because you need more material, and it's probably won't fit, right? And so you want to, and sometimes having a heavier design is not good, especially when you want to design things which move. If it's stationary machinery, it might just be okay, but also the cost increases as you make things heavier. So there are a lot of decisions to be made. Anyway, so let's see how we can apply all these things into one problem. So here is a problem which sort of helps you to understand how these equations are used. So steel bar undergoes cyclic loading. Question. Can we just use the line that is least conservative all the time? Yeah, so the problem with using the least conservative line is that the more conservative you get, the higher the design, the factor of safety, and higher factor of safety means that your design is going to be expensive, it's going to be heavier, and you don't want those things, especially for certain applications like, I don't know, for aerospace applications, you want the design factor to be as low as possible. So it just depends on what are your constraints as a designer. Okay, a steel bar undergoes cyclic loading with nominal stress at the notch given as sigma max equals 60 kpsi and sigma min equals minus 20 kpsi. So sigma max is 60, sigma min is minus 20. Stress concentration factor Kf equals 1.2. The ultimate strength is 100 kpsi. Yield strength is 85 kpsi and fully corrected. So this is not SE prime, but SE. It accounts for all the imperfections. And then estimate the infinite life factor of safety, which is essentially saying find NF using the Goodman line, Gerber line, Soderberg line, and ASME-Elliptic line. Okay, so if you look at those equations, all those equations involve, so we need S sigma A, sigma M, SUT, SY, SE. And these are the things we need in order to find the factor of safety for fatigue life, right? And so we know all these, well, the last 3 things. We do not know sigma A, sigma M. And there's another thing which you need to account for, which is the fact that there is a stress concentration The geometry of the stress concentration due to which there is a factor of uh, the stress concentration due to fatigue. And we need to account for that when we compute sigma A and sigma M. So let's first find sigma A, sigma M when there is no stress concentration, right? So the nominal value. So I'm going to denote that as sigma A nominal, and that is by a formula sigma max minus sigma min divided by 2. That's just the definition of sigma A. So 60 minus, sorry, minus 20 divided by 2. So that's 40. Then sigma nominal is sigma max plus sigma min divided by 2. That's 60 minus, so 60 plus minus 20 divided by 2, and that's 20. Okay, and so if that's the nominal stress, if you want to find the maximum stress, it's simply the factor of fatigue failure times sigma A nominal equals 1.2 times 40, which is 48. Sigma M equals K F sigma M nominal, which is 1.2 times 20, which is 24, and this is K PSI, K PSI. Okay, so we have sigma A, sigma M now. It's a matter of using the equations to find the factor of safety. So let's use the Goodman line. Goodman equation. So that says that NF equals sigma A divided by SC plus sigma M divided by S ut negative 1 equals sigma A is 48, SE is, see, SE is 40, okay, 40 plus sigma M is 24, SUT I think is 100, comes out to be 0.69. The Gerber equation is stored on a new page. Big equation. Okay. Okay, so let's sub in. SUT I think is 100. Sigma M was 24. Okay. Sigma A was 48. SC was 40. This one plus 2 times 24 times 20 divided by 48 times 100. Okay, so doing all the math, get 0. SCF. So it's right in my notes. It's 0.8, I believe, is the answer. Okay, the next are kind of easy. C. Let's do the Soderberg. And that's simply NF equals sigma A divided by SC, sigma M divided by S Y. This one equals 48, 40 plus 24, 85, 85 inverse 0.67. Okay, the last one, ASME-Elliptic. Okay, so let's summarize what we have. Goodman, Gerber, Soderberg, ASME-Elliptic. So 0.69, 0.8, 0.67, 0.81. Yes, for this is the most conservative, and this is the least conservative.